So, our last topic on acids and bases is something entirely different, which is buffers. So, a buffer solution is something that resists large changes in pH when a small amount of an acid or a base is added. So buffers work because they contain equal amounts of weak acid and its conjugate base, or weak base and its conjugate acid. And what that means is that you will react with the added hydronium or hydroxide to minimize the pH change. Now, what does that mean? Well, an acidic buffer is something that works in the acidic range of something like pKa less than 7, okay, or a pH less than 7, until you understand what pKa means. So something like this H2CO3, which I think is carbonic acid. H2, yes. So carbonic acid in water produces this hydrogen carbonate ion. I believe that it's what it's called. Yep. And hydronium. Versus a weak base would be something like a carbonate ion accepting a hydrogen from water and forming this hydrogen carbonate conjugate acid and hydroxide. So this is an example of an acidic buffer. This is an example of a basic buffer. Now I couldn't just reverse this because there's something very specific about something that makes it basic. It's not just that you've started with a base, but we want an acidic buffer to start with an acid. We want a basic buffer to start with a base. Okay. And the important thing about forming a buffer is that you will always have a conjugate acid base pair, conjugate base acid pair, and they will be in equal concentration. So there's a few multiple choice questions where it's like, which of the following could be used as a buffer? Just make sure they're weak and make sure they're in conjugate pairs. Okay, now let's talk about what makes something actually an acidic versus a basic buffer, and that is its pH range. So to find the range of pH values for a buffer. I've been making videos for 4 hours. I'm starting to go crazy. But to find the range of pH values for a buffer, we're going to use the Ka values. So let's look at an example of CH3COOH. So let's look at an acetic acid buffer. So this is the acid and its conjugate base present in equal concentrations. We would say that acetic acid plus water forms hydronium and CH3COOH, which I believe is, I don't even want to guess. Okay, whatever, doesn't matter. But the Ka expression would be CH3COO minus times hydronium divided by the acetic acid. But there's a condition here. Since the acetic acid and its conjugate base are in equal concentrations, we can actually cross them out and say that the Ka value will equal the hydronium concentration in solution. So if we then took the negative log of the concentration, and what we do to one side, we do to the other side. So we're going to take the negative log of Ka. Oh, there's that pKa. And we would get that pKa is equal to pH. So if you want to find the range of pH values that your system buffers, it's based on your Ka, but then you're going to change it into a pH. So let's look it up. The Ka value of CH3COOH is what? CH3COOH is here, which has a Ka value of 1.8 times 10 to the negative 5. So 1.8 times 10 to the negative 5. Treat that like a concentration, and we're going to find the pKa. So we're going to take the negative log of the Ka, which is going to give us negative log of 1.8 times 10 to the negative 5. Okay, so negative log, I keep switching calculators and they're all in different modes. So I'm going to do negative log of 1.8 times 10 to the negative 5, which is going to give you a pKa of 2 sig figs, 2 decimal places, 4.74. So now this is going to be an acidic buffer because it is has a pH less than 7. So since pH or pKa, either one, is less than 7, this is going to be an acidic buffer. And then the range of pHs that it would buffer is going to be plus or minus 1. So it's going to go from 3.74 to 5.74 would be the range that this buffer would work in. Okay. Oh, so within a range of 3.74 to 5.74. That's what happens when I just make the notes. I forget what spaces I've put in here. And we would call this an acidic buffer. Easy peasy. All right, so our next question is, which weak acid and base pairs on the relative strengths of Bronsted-Lowry acids and bases could be used as acidic buffers and basic buffers? So we were talking about how an acidic buffer can be used for anything with a pKa or a pH that's less than 7, and that a basic buffer is anything that can buffer something with a pH greater than 7, right? We should actually say pH, make it easy, right? Let's just not try to make this complicated. Now, what is kind of complicated about this is that to have a pH less than 7, then you're going to have a Ka that's actually greater than 1.00 times 10 to the negative 7. I'm not going to get into a lot about why, but just think about that. When we have that relationship of pH and hydrogen ion concentration, the greater the hydrogen ion concentration, the lower the pH. So it's the same idea. The lower the pH, the higher the Ka value. And then these ones are going to be Ka values that are less than 1.00 times 10 to the negative 7. Okay? Because these guys are going to be stronger bases and these guys are going to be stronger acids. So if you look at the table, right, and we look to see where the split's going to be, we've got this 1.0 times 10 to the negative 7. That's technically where the split would be. And all of these guys above would be acidic buffers because they're all stronger acids. Whereas all these guys down here would be basic buffers because they are stronger buffers. So we could say anything, greater than 1.0 times 10 to the negative 7. So monohydrogen citrate ion all the way up to the the iotic acid, or simply we could just say iotic. So that HiO3? I think that's what it is. So from HiO3 down to that HC6H5O72 minus. I'm just not flipping between because I'll never remember that formula, which is the dihydrogen. Ooh, this is such a fancy one. Dihydrogen citrate ion. So everything from iotic down to dihydrogen citrate is going to form an acidic buffer. So they're conjugate pairs. And then the basic buffers would be anything from, so you're going to look from that point down. I've lost it. 1.0 times 10 to the negative 7. There we go. So we're going to go maybe from the H2S all the way down to the HPO4 minus. Maybe down to the water, but let's just put the HPO4 minus to be safe. And you're not going to be tested on this. It's just kind of understanding that there are things that can buffer acidic situations and there are things that can buffer basic situations. All right, now the questions that you're actually going to be asked on this is not which ones could be acidic and which ones are going to be basic, but actually how to prepare an acidic buffer and how to prepare a basic buffer. So for an acidic buffer, we're going to prepare a buffer that buffers with a pH of 6.3. So to figure out which acidic buffer we're going to use, you're going to say that if the pH is 6.3, then the pKa is also 6.3. So then what we want to do is find the Ka value by doing 10 to the negative 6.3. It's like going from pH to concentration. We're going to go from pKa to Ka. So we're going to plug this into our calculator and we get 10 to the negative 6.3, which is going to give us a Ka value of 1 decimal place, so 1 sig fig, 5 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. So we want to buffer somewhere in the 5 times 10 to the negative 7 or something with a Ka around there. So then we're going to go to our information booklet. So then what we're going to do is we're going to go to our information booklet and we're going to look for the conjugate acid-base pair that has a P or a Ka closest to 5 times 10 to the negative 7. So this is my group of times 10 to the negative 7s in here. So the 5 times 10 to the negative 7 is going to be the closest to 4.3 times 10 to the negative 7. So my acid-base pair is going to be my carbonic acid and the hydrogen carbonate ion. So the H2CO3 and HCO3 minus has a Ka value of 4.3 times 10 to the negative 7. So that's going to be the closest. So to prepare this buffer, add equal concentrations, oftentimes we'll just say 1 molar, so equal concentrations of H2CO3, and now here's the very important thing, is that this is your conjugate base, and we need to add it, but it's an ion, and you can't just add ions to solution. So you would have to add or combine this with a cation that's going to keep it soluble. So I'm going to add sodium to it to form sodium or NaHCO3. So I'm going to add equal concentrations of H2CO3 and NaHCO3 to solution. And that's how I'm going to create this acidic buffer. So just be careful anytime you're adding ions to solution, make sure you add them as a salt, right? So make sure you add some sort of soluble ion that's with it. All right, you can pause the video and give this one a go, but we're going to prepare a basic buffer. So again, with this one, they're going to give you a pKa of 11.3, which is a pH greater than 7, which makes it basic. So if we want to find the Ka, we're going to do 10 to the negative 11.3. When I plug this into my calculator, I get 10 to the negative 11.3, which gives me, again, to 1 sig vig, 5 times 10 to the negative 12. So then we go to our information booklet and we look for something that's close to 5 times 10 to the negative 12. This 2.4 times 10 to the negative 12 is going to be closest. So we're going to use hydrogen peroxide and its conjugate base. So we're going to use H2O2 and HO2 minus, which has a Ka value of 2.4 times 10 to the negative 12. That's as close as we could get. But remember, this is going to buffer plus or minus 1 pH. You just want to go closest. So to prepare this buffer, add equal concentrations of H2O2, so that hydrogen peroxide, and now let's make this into a salt, so I'm going to always add sodium. So I'm going to add sodium, or NaCO2, and then I don't put the minus charge anymore. So just make sure you're using a conjugate acid-base pair that is closest to that pKa or Ka value, and then just make sure that you don't add any ions. Make sure you add them as salts.